Welcome to G Fun Facts Online. What if, in the middle of a cross-country road trip, your GPS just went dark? No signal, nothing. Or what if you're a pilot and your navigation system starts feeding you false information? It sounds like a scene from a spy movie, but our complete reliance on the global positioning system makes this a very real and very scary possibility. We use it for everything, from finding the nearest coffee shop to guiding jumbo jets and massive cargo ships. But what happens when it fails? Well, the answer might just be found inside one of the most glamorous materials on Earth, the diamond. You see, GPS signals, beamed down from satellites orbiting high above us, are surprisingly weak. They can be easily jammed, deliberately spoofed, or simply unavailable underwater, underground, or even inside large buildings. The classic backup is something called an inertial navigation system, or INS. It's basically a clever box with gyroscopes and accelerometers that says, okay, I know where I started, how fast I am going, and in what direction, so I can calculate where I am now. The problem? Tiny errors build up over time. It's called drift, and soon enough, that INS thinks you're in the next town over. It needs a regular GPS fix to stay accurate. But what if we could build a compass so unbelievably precise that it could navigate not by satellite signals, but by the Earth's own magnetic field? And what if that compass was built from a diamond? Not a natural one from a mine, but a lab-grown, perfectly engineered diamond with a very specific, intentional flaw. This is where we get into the mind-bending world of quantum physics. Scientists create these diamonds and introduce a tiny defect called a nitrogen vacancy center, or NV center. They take out a couple of carbon atoms and pop in a nitrogen atom right next to an empty space. This tiny flaw acts like an artificial atom, and its electrons are incredibly sensitive to magnetic fields. Here's the simplified version. They shine a green laser on the diamond, which gets the electrons all excited. Then, they zap it with microwaves. The exact microwave frequency needed to flip the electron's spin depends directly on the strength of the magnetic field around it. When the electron flips, the red light it glows with dims slightly. By finding that exact point where the light dips, scientists can measure the magnetic field with breathtaking precision. It's a quantum compass. And the best part? It works perfectly at room temperature. So how does a super-sensitive compass help you navigate? Well, the Earth's magnetic field isn't uniform. It's full of tiny bumps and wiggles, unique magnetic signatures all over the globe. If you have a highly detailed map of these magnetic anomalies, and your vehicle has a diamond magnetometer, it can constantly read the local magnetic field and compare it to the map. Just like you might use a mountain peak as a landmark, the system uses a unique magnetic signature to pinpoint its exact location. It's completely passive. It's just reading the environment, which means it's impossible to jam or spoof. This solves the two biggest problems. First, it gives navigation systems an unjammable backup for when GPS is denied. Second, if you pair this diamond magnetometer with a traditional INS, it can constantly correct for that pesky drift. The magnetometer provides a steady, accurate reference from the Earth itself, keeping the entire system on track, indefinitely. And this isn't just theory anymore. The tech is shrinking fast. The Fraunhofer Institute in Germany made their quantum magnetometer 30 times smaller in just 1 year. The Canadian and European space agencies are testing these sensors in the harsh environment of space. And, in a project with the very cool name Dark Ice, defense contractor Lockheed Martin is developing this for covert military navigation. Beyond just finding your way, the applications are incredible. These sensors can map the Earth's crust to find mineral deposits without drilling, or even detect unexploded bombs. In medicine, they could monitor the heart's magnetic field with more detail than an ECG. We're talking about a new tool that could change everything from geology to medicine to space exploration. Of course, there are hurdles. The technology is still expensive, and we need to build out those ultra-detailed global magnetic maps. But the progress is incredibly fast. We are on the verge of a navigation revolution. A future where getting lost, whether you're a submarine deep in the ocean or a self-driving car in a city canyon, becomes a thing of the past. And it's all thanks to a tiny, perfect flaw in a lab-grown diamond, proving that sometimes our greatest strengths can come from our imperfections. Thanks for tuning in. Until next time, stay curious.